All right, folks, so here we are, lecture 4. We are talking again about relationships. You know, with lecture 3, that began our discussion of relationships. We did it through contingency tables, and therefore we looked at categorical variables. Today, we're looking at interval variables and learning how to find and interpret the relationships between interval variables. Skip this over. Okay. So scatterplots. Scatterplots show a relationship between two interval level variables. In a scatterplot, every case appears as a point on a graph. So, for example, we have two interval level variables for 16 students. So we asked 16 students, how many martinis did you drink? And then we measure their blood alcohol content. So we can see here, student 1 had 5 martinis with a blood alcohol content of 0.1, and we can read that all the way down to student number 16. So we're interested in the relationship between the two numerical variables to see how one is affected by changes in the other. Right, and so this just helps us visualize what we are going to be doing. From this table, we'll be able to create a scatter plot, but ultimately be able to understand the relationship between the two variables. Okay, and our two variables, hopefully we know, it's the number of martinis, so that's one question. Second question, blood alcohol content. So the scatter plot is a representation of those 16 students. We asked those two questions, and we can see here that it's a scatter of points, where each point denotes the values of an observation for two selected variables. So each point in the graph corresponds to the 16 students from the table in the previous slide. So we can see person number 1, who wasn't person number 1 in the previous one, I believe, because they had 5 drinks. I don't remember. Anyways, let's take a look. Person number 1 had 5 drinks. Yes, ooh, I'm good. So this x-axis isn't necessarily person number 1 and so on, right? So we can see it's just the number of martinis. We're making that our independent variable because we know independent is the one that sort of helps us determine what the dependent variable is. Said another way, the dependent variable is waiting to see what the independent variable will do, and then it determines, right, what the value of that dependent variable is. So person with 1 martini, blood alcohol content was 0.01. Person with 5 martinis, varied, right? One person had 0.05, another 0.06, another 0.08, another 0.1, right? So it varied. And then person number, one other person had 9 martinis. We're not going to judge because that could very well be your professor with the 9 martinis, but she can hold it down even though her blood alcohol content is 0.19. So we can see that that table is represented here in this chart. Okay, so moving on, scatter plots, what do they tell us? Okay, scatter plots tell us about the overall pattern of that relationship. What's the form, what's the direction, and what is the strength of the relationship between the two variables. In terms of direction, we're always going to think positive, negative, possibly no direction. But there's always a direction, to be honest, because, we'll hold that thought. Positive, negative, or no direction. We'll stick there. And then strength, we're looking at how closely the points fit on a straight line, or how far apart, how spread out they are, how scattered they are. And then form. So there's different ways it could be. It could be a line, it could be curvilinear, no pattern at all. And then, of course, these these variables, their values could have some outliers. There could be strange deviations from the pattern. Consider the example here. Maybe the person who had 9 martinis might be an outlier, right? Because we could see a line possibly going through here, and this person is sort of outside of that line. And so we might say that the direction is positive, right? Because as this is going up from 0 to 10, right? As x-axis is going up, y-axis is also going up. And then the form, it's a straight line. It's not a S, it's not a V, it's not a U, it's just a straight line, right? So let's look at other examples of direction. So in terms of direction, if your x-axis is going up and your y-axis is also going up, that's a positive relationship. In terms of direction, as your x goes up, if your y is going down, that's a negative relationship. Ooh. Okay. Man, that light was too much. Okay, so we can see here, if you follow the mouse clicker here, you'll see that as x is 1 and it goes to 2, as it goes to 3 and 4, right? So we're seeing x going up. But what happens to y? Well, y starts off at 1, then it goes to 2 when x is 2, then it goes to 3 when x is 3, right? So we see that it's going from left to right, it's going up, right? And we can see our negative relationship. X, again, is still going from 1 to 2 to 3 to 4 to 5, right? All the way to 10. But as x is going up, increasing from 0 to 10, what's happening with y? Well, it looks like y started off really high, but now it's decreasing for every time x increases. So that is a perfectly negative relationship, okay? And so here we have no relationship, because as x goes up, what happens in the first instance? For example, x goes up, y goes up. But then x goes up again, what happens with y? Well, based on this, that second dot here, x goes up slightly, or it could go down, right? What happens with the next set? So x goes up again, y is going up, right? But then in the next set, y can go up or down. So we have no clue what's happening. We have literally no clue whether this is a positive or negative. What we do see is a straight line going through, and that's indicative. That essentially means no relationship. When you could draw a straight line through, what does that mean? As x goes up, what's happening to y? Y stays the same, or y does not change based on x. So that's another way we could say that. Y is not changing based on x. Maybe another x, but this particular x, y is not changing based on it. Okay? And so, again, here's an example of, oh, what just happened? Here's an example, I'm sorry. Here's an example of no direction again, right? In the first one, we see as x changes, it's going up. What's happening with y? Doesn't even change. So x changes, y stays put. So there's no relationship there. What happens here? This is similar in the second one as what we saw in the previous slide. As x increases, y just does whatever the heck it wants to do. Okay, so an example of no direction and no relationship is knowing that x tells you nothing at all about y. In both examples, x and y vary independently. Okay. All right, so now we've talked about direction, so let's talk about form, what the scatter plot looks like. We can see form of lines, right? Linear forms. We can see from that dotted line, these are just the same graphs, and I just place a dotted line in the middle to show you where that plot might land, right? Where the form is for that scatter plot. And we see at the bottom with the curvilinear relationship that plot would be a U shape, right? A U shape, and we have relationships that tend to be U-shaped. Age is one of them, is one that comes to mind quickly, because we've seen in research that there are certain things that maybe middle aged people might engage in, but younger and older citizens might not engage in, right? Something like a PTA where middle-aged people have young children, whereas seasoned citizens and young adults, 18, 19, might not have children. And if they do, they're probably not concerned about PTA at the time, because they're probably also in school themselves or in college or something, right? So there are situations where we have curvilinear forms. In this case, it's a U shape. It could also be a N shape. It could be a S. I mean, we could see lots of different forms, okay? And then the last thing that a scatter plot can tell us: direction, form, and now strength. This is just as important as all the others, but this is what this tells us whether it's a strong, moderate, weak relationship, whether it's no relationship at all, right? Just like direction can also help us with that. So when it's a strong linear relationships, the points will all seem to be grouped fairly close to a line. So we can see that here in this first plot. This one is a pretty head-on, dead-on relationship, because as one increases, the other increases exactly the same amount. So that's a very strong relationship. We can see weak relationships in the second plot here. Now, the weaker the linear relationship, the farther apart the points will tend to be from the line, and harder it will be to see where that hypothetical dotted line is that I've been drawing. Okay, and we've talked about no relationship, so I won't beat a dead horse, but let's look at this weak relationship, okay? So we can see here that, yes, there's some variation in what happens to Y when X changes, but one thing we can definitely see, right, we can see that a line would go through right here. It wouldn't go from left to right down, it would go from left to right up. So we can actually see where our hypothetical straight line would be. We can see that, but it's just clearly more spread out than the strong relationship, right? All right. And so here's an example of strength. Again, I want us to like pick through this together. To the left, would you say that's pretty spread out, or very close together? Would you say, what about the second one on the right? Which one is stronger? Which one has a stronger relationship? These are two completely different sets of variables, right? The first one looks at state per capita income as it relates to state median household income, right, by the thousands. And the other one looks at average amount of gas consumed per day in hundreds of cubic feet, where as it relates to average number of heating degree days per day. So which of these has the stronger relationship? All right, so I've provided some of my feedback. Others might look at what I said and say, no, don't agree with you there. So I say the one on the left is moderately strong. So median household income can predict state per capita income, but not as well as, say, daily amount of gas consumed can predict, accurately predict given temperature value. So that's my thought, but we might disagree. And it's in that disagreement that comes this awesome number called the correlation coefficient, or we just say R. R. Correlation coefficient, or we just say R. Because there are instances where we both look at where everyone in the room is looking at this graph and we go, nope, that's a weak relationship. Nope, I think it's moderate. No, I think it's pretty strong. So we try to get rid of these inconsistencies in how we're thinking about a variable, about the relationship, by using a correlation coefficient, which we all agree on what that number will mean. Okay, so let's talk about this, because relationships are complicated, folks, and we want to simplify it as much as possible, right? By being on the same page, by using one number and determining what to do, what that number means. So correlation coefficient is a single number summary of a scatter plot. It never conveys as much information as a full scatter plot. It only summarizes the information in the scatter plot. However, it is often more convenient to report a table of correlations for many variables, right, than to report an unwieldy number of scatter plots. Imagine we have 10 different relationships we want to look at between these two variables and these two variables and then these two variables 10 times, right? So 10 different couples that we want to examine, okay? And we decide to create these huge tables, graphs, or we just create either 10 graphs or a table with 10 numbers. Which one would be most time efficient and confusion efficient, decrease confusion, right? Probably the table with just 10 numbers, and we just all agree on what those numbers are. So intuitively, the relationship is strong if the points in the scatter plot cluster tightly around some straight line. Okay, we know that because we've gone through that in the previous slides, right? If the straight line rises from left to right, right, the relationship is positive, and we would therefore see a correlation coefficient with a positive number. Just that simple, right? As X is going up, Y is also going up. That's a positive relationship. Our correlation coefficient, in a nutshell, would spit out to us a positive number. Now, if it's a negative relationship, right, from left to right, left to right, that number is falling, right? Then we have a correlation coefficient that should be spit out to us with the negative sign beside it, right? So now the correlation coefficient is telling us what we would have already seen in the graph, okay? And some other guiding principles. So we've talked about direction already. Direction should always mean to you positive or negative. If ever someone asks you, what is the direction of this relationship? The only words that should ever come out of your mouth is the word positive or the word negative, okay? And we know, because we know basic math from elementary school, that if it has a negative sign, it's a negative. If it has a positive sign, it's a positive. If it has no sign, it's also a positive. So positive relationships, again, repetition is good because we are in a learning process. So we're going to repeat and really get this in our system. When an independent variable increases, that dependent variable is decreasing, right? When that x-axis is increasing and our y-axis is increasing, positive. On the contrary, our x is going up, our independent variable is going up, and our dependent variable is going down, negative. Let's think about this, okay? In a real relationship, right? If we're saying that we're doing so well together, everything's going well, we're getting along, right? That means we are thinking on the same wavelength, or we are in agreement, right? Things are going well, we're in agreement. So I'm going up, you're going up. If I'm going down, and you ride or die, you're coming down with me. You're like, I'm with you. I'm with you. That's still a positive relationship. Just because we're both going down doesn't mean it's a negative. Things might not be good, but it's still a positive relationship. We're going in the same direction. Okay? Negative relationship, I'm going up and you're going down. I'm going left and you're going right. We are not seeing eye to eye. We're just not. right? That's a negative relationship. I don't get why he doesn't get me. Right? Negative relationship. Okay. I'm going down, he's going up, right? I'm going up, he's going down, right? Or she, my sister, my mom, whoever, right? So, if we're not in agreement, we're not going the same way. Negative relationship. Okay. So we've talked about direction. Now let's talk about strength. In terms of strength, we have a guiding principle, and this is the crux of why we even use this correlation coefficient is because, as we saw in the previous scatter plot, I said it was strong, you said it was moderate, someone else might have popped in and said, what are you guys talking about? This is a weak relationship. So we have guiding principles about strength. So the first thing we know is that strength, the correlation coefficient, first off, goes from, it could be a -1 all the way to a +1. What does that mean? -1, -0.9, -0.8, -0.1, right? It can go to, it could be a 0, which hopefully, which definitely means no relationship, because that's what 0 always means. No, zip, zilch, null, none. And it could all, those numbers could also be positive, right? But so 0, as I said, no relationship. R, that's a +1 or a -1. R, that's a 1, period, has the strongest possible relationship. So the strength is based on absolute value. So while we do have a range of R can be negative or it can be positive, that's direction. That's direction. Okay, but strength is based on the number, whether or not it has a positive or negative sign on it. So the number, the number 0.29 is a weak relationship. The number -0.29, what type of relationship is that? Well, based on this rubric that we're looking at, based on these strength levels, it's also a weak relationship. Because if you look here in parentheses, strength is based on the absolute value of the number. So if the number is -0.25, then that's the strength, the direction might be negative, right? But the strength, 0.25, we know is weak. Okay? So I put here in this shrinking text here, because it's critically important that we understand the difference between strength and direction. Direction only has to do with whether a number is positive or negative. Strength, however, has nothing at all to do with whether a number is positive or negative. Again, I say, strength has nothing at all to do with whether a number is positive or negative. Strength has to do with whether that number, positive or negative, regardless of what it is, if it is in these brackets, then we call it whatever that is, right? 0.31, that's a moderate. -0.31 is a moderate relationship. So a number 0.29 and a number -0.30, which one is stronger? Well, 0.29, yes, it's positive, but who cares, right? Because we're only concerned with strength, not direction. And then -0.31, moderate. Positive 0.29 is weak. -0.30 is moderate. Who cares if it's negative? The strength of the relationship is positive, is moderate, so it's stronger than a relationship that's 0.29, right? Because that number, absolute value of that number is higher. 0.30 is higher than 0.29. I hope that I've stressed that enough, because I've been teaching this since 2012, and half of the class just cannot, they grapple with this. So it's such a hard concept to understand, to just get it in your system. But know that just because a number is negative, it does not mean that that number is now weak. Does that make sense? Just because a number is negative does not mean that its strength is now weak. because we see here in this little chart, this little guide here, that there's nothing here about negative, right? The number goes from 0 to 0.29, okay? 0 to 0.29, so that's, you know, that's the lowest number a strength can be, 0 to 0.29. So if the number has a negative sign beside it, then clearly the signs don't have anything to do with strength, only direction. Okay, I will leave this point alone. All right, so let's do some practice. The next two slides are all about just practicing how to interpret these numbers, because we can now interpret strength and direction, right? Form is only something that we can observe through a scatter plot, right? Strength, direction, we can observe in a scatter plot and in a correlation. Form only with the scatter plot, because these are numbers. I'm not sure, they don't wiggle and squiggle around, so we can't see if it's linear or curvilinear, right? So, or no, nothing at all, right? So in terms of direction, we can see, do we see any negative signs here? If we don't see a negative sign, then that means what? That means that all of the relationships in this correlation matrix, we call it a correlation matrix, all these numbers are positive, have positive directions, okay? So let's take a look at this correlation matrix. Every number in here is called R. Every number in here is called a correlation coefficient. Remember, they're the same two words, R or correlation coefficients, okay? So 0.911, positive or negative direction, positive. 0.911, based on this here, is that, what strength is that? 0.911, we would say strong, right? If it said negative 0.911, hopefully we would also say strong, and we would be correct. 0.911, negative 0.911, both would be strong. Okay, let's go to the next one. 0.606. What does that mean in terms of direction? Positive. What does that mean in terms of strength? Well, let's take a look. 0.606, again, we would have a strong relationship. In terms of direction, it's positive. In terms of strength, it's strong. All right, so really quickly, let me take a step back and talk about what we're looking at in this matrix. Okay, correlations, obviously all the numbers are correlations. All the words are the variables. It's a matrix, so what you see after this one, everything to the left of this one is a duplicate of everything to the right of the one. What do I mean by that? 0.911, the relationship between salary and grade, pay grade. Here's 0.911 again, relationship between salary and pay grade. So everything we see on the on one side, it's a mirror image of the other side. 0.606, education, relationship with pay grade. Let's see, education, relationship with pay grade, we see again 0.606. Okay? Yep. So now we know that these are all variables. All these numbers are correlation coefficients, right? And what are these ones, though? Goodness, what does this one mean besides just a demarcation of the mirror image, right? These ones mean that if I'm looking at pay grade if pay grade, is looking at pay grade in the mirror, it should see itself. It should be a one-to-one relationship. If pay grade takes one step, what should the other pay grade do? Take one step. It's the same thing. It's not the other pay grade. So I shouldn't have even said that. It's the same. I'm looking at pay grade in the mirror. Okay, that's it. It's an identical thing. So the relationship would be one-to-one, because we know, what did we say? One is the strongest possible relationship that ever exists, whether it's -1 or +1. But because pay grade is looking at itself in the mirror and not looking at its nemesis in the mirror or something, this is not some spooky craziness. No, pay grade to pay grade is 1. Salary to salary, right? Salary to salary is 1. And we can continue. Education to education is 1. Federal years of service to federal years of service is 1. What about age? Age to age is 1. So the computer spits out a 1 because it says, this is the strongest relationship I've ever seen. Well, duh, it is, because it's looking at itself. It's looking at itself. But then it starts looking at other things, other people. It says, what's the relationship with salary and pay grade? Well, as salary increases, pay grade increases. If we know what pay grade means, pay grade are groups of salaries, right? Someone with a pay grade of 11 is not going to be making $35,000. So yeah, someone with a pay, so the higher your pay grade, the higher your salary. They will correlate very strongly with each other. Now, pay grade and salary do overlap, right? But for the most part, pay grades overlap with themselves. So, but for the most part, as salary goes up, pay grade should go up. We can say it the opposite way. As pay grade goes up, salary goes up. We can even say it a different way. As pay grade comes down, salary comes down, because these are positive relationships. So if I'm going down, you're coming with me. Man, that's something serious, right? Great, strong, positive relationship. Okay, so let's take a look at the relationship between pay grade and age, for example, or education. The higher one's years of education, the higher their pay grade. So that's how we interpret this. We don't just talk about strength and direction, but we need to be able to go out on the street or go home to mama or go somewhere where someone doesn't know anything about statistics and say, hey, did you know that as the more education that you get, the higher your pay grade is, and that it's a pretty strong relationship? Right? That's a whole lot more, makes a whole lot more sense than someone saying, oh, did you know that education and pay grade are a positive, strong relationship? Thanks. I don't know what that means, but thank you. I know what it means. You know what it means, but the person who hasn't taken stats or hasn't taken this course, right, might not know what positive, strong relationship means. So we put it in layman's terms. We as public managers, we as regular normal people put it in terms that other people can understand, and not always this statistical jargon. Okay, so as education increases, pay grade increases, and it's a pretty strong relationship. As education increases, as age increases, right, salary increases. Well, let's take a look. Age and salary, it's still positive, yes. And the relationship, we can say 0.29 is weak. So it's right there at the border, but we'll call it weak because we are all on the same page on what we're going to call it. And this is for this class. And I know people, other fields that use this, this might differ by field, right? 0.7 might start strong relationship in some fields, in some offices. It's up to, you know, the field and the what's the word, the popular way of doing it for a specific discipline, if you will. But for this course, so that we're all on the same page, we're calling 0.29 and lower weak, 0.3 to 0.59 moderate, 0.6 to 1 strong. Okay, so the older you get, the higher your salary will be. But not by much, right? Because this is a weak relationship, okay? That beats going out on the street and saying that age and salary is a positive, weak relationship. I promise you most people won't know what that means. But we put it in this very basic layman's terms so that we're all communicating and understanding the communication. So then I'll let you try this one, age and years of service. Okay, that number would be age of years of service, 0.621. So how would we interpret that? Hopefully we would start with direction and say it's positive because we see everything here is positive. We would then talk about strength. We know that 0.60 and above is strong. So we're going to say this is a strong relationship. But guess what? We're not going to stop there because we know that there's a better way of saying this. So as one gets older, the older you get, right, the higher your age, the higher your years of federal service, okay? The higher your age, the higher your years of federal service. And what about grade and salary? Well, we've already done that. The higher your grade, the higher your pay, your salary. And the one thing I want to point out here is that there is, I've provided a very simple, because my mind thinks in equations. So I've provided a word equation, if you will, under the notes here for how we interpret two interval variables, okay? So we essentially say as, and we say the variable. As if our R here for age and salary is 0.32. If that's the case, we don't see that in the table, but if that's what we see in the table and it's positive 0.32, then we would just plug into that equation as age, we would plug in age. As age increases, we would then plug in what's our next variable? Salary. Then salary, what happens? We base it on whether the sign is a positive or a negative. So as age increases, salary, this is a positive number, so we'll say increases. Now let's take, for example, that R ends up being negative. The only thing changing here, as we're going to say age again, as age increases, what happens with salary? Salary, because it's a negative sign, we're going to go with decreases, okay? So another way we could say it, because you don't have to say everything the same way, right? I can say as age increases, salary increases. Someone else might want to say the higher one's age, the higher one's salary. And there's even more other ways, right? The older one gets, but for the sake of providing you with a generic form that you can literally complete for everything that you have a correlation coefficient for two interval variables, I provide these two examples, okay? These two word formulas where you literally type in the word for whatever the variable is, okay? So the next example, the higher the blank, variable one, we're gonna say age. So the higher the age, and here we are again, having to choose between higher and lower. Because it's a positive number, we're gonna say higher. Okay, and the second variable is salary. So the higher the age, the higher the salary. Again, we go to the second example. It's a negative sign now. So the higher the age, the lower the salary. Just that simple. Literally just that simple. So follow this rubric, follow this word equation, and I promise you there's no going wrong. There's absolutely no going wrong, okay? Because we use that equation for literally everything, okay? Oh no. Wait, let's see what happens. There we go. Okay, so the higher the years of service, what happens with pay grade? The higher the pay grade. And this is a moderate relationship. So we make sure that we tell them, you know, it's moderately strong. Okay, not strong, not weak, somewhere in the middle. So now those are examples of two interval level variables. These are all interval level to another interval, right? To another interval, say 10 years of education, 12 years of education, right? Years of service, you know, I've worked here 35 years and I am 35 years old, right? So these are interval variables. And we know that dummy variables, we can code dummy variables because we've done it in our homework. In order for the computer, Excel, calculators to understand anything, what they should do, right? We need numbers. So the variable gender, we recode it to be 0 equals female, 1 equals male. We could have recoded it to be the variable female, where 1 equals female, 0 equals male, right? So that's not a big deal. If we did recode it that way, just a quick rule, just a quick rule, when you do recode it, as long as you code correctly, you will always have the same answer. So in this case, we would have had a negative 0.361 if we had recoded so the variable is female. Okay, and I'll speak more about that at the end when we're interpreting. So another correlation matrix. How many variables do we have? 1, 2, 3. One variable salary, another gender, another race. Okay, what else do we see? A whole set of numbers, right? And we see the ones because it's one-to-one relationship with itself, right? One-to-one relationship with itself. What's the relationship between salary and male? What's the correlation coefficient? Well, it is 0.361. Salary to gender, 0.361. Notice that I'm saying gender, even though we don't see that word anywhere. But we know this is not a variable we know that this is not a variable that's only concerned with male, right? But we call it male because that's the way that we remind ourselves without even having the codes on the screen, right? That this variable was coded 1 equals male. It's a dummy variable. Only dummy variables get coded with that in this way. Only dummy variables, okay? So the relationship between the R for salary and gender is 0.361. The R, or the correlation coefficient for race and salary, is a negative 0.233. So I ask, what is the direction of the relationship between gender and salary? Well, 0.361 is a positive relationship, so we're going to say the direction is positive. What about the direction between race and salary? The direction we see is negative because there's a negative sign, so it's that simple. It's a negative direction. What about strength? Okay, well, in terms of strength, 0.361 is moderate. 0.233 is weak. Not because it has negative, but because the number 0.233 falls between 0 and 0.29. That's it, right? The negative only tells us direction, okay? And then we'll look at the correlation coefficient for gender and race later. Okay, so how do we interpret this? It's different. It's a different way of interpreting when it comes to one interval variable and one dummy variable. It's different because in this scenario, now it's a comparison. We're comparing the two values in that one dummy variable, the two values being male and female, the two values being white and black. We're comparing those two groups and their salaries. What's male salaries? What's female salaries? We're comparing. So in our comparison, the words female and male must be in the interpretation. The word white and black must be in the interpretation. Obviously, also the word salary in the interpretation. So let's take the first one. Males have higher salary than females. That's how we're interpreting this. Do we say the higher the male, the higher the salary? Because, that's kind of how we talked about two interval variables. We said the higher the age, the higher the pay grade. The higher the years of service, the higher the pay grade, right? The higher the education, the higher the pay grade. The higher the salary, the higher the pay grade. It was very simple. It was very simple, right? We didn't have to say as it goes from 10 years of education to 11 to 12. We just said the higher because this is a positive relationship. The higher it is, the higher our pay grade. Well, here we can't say the higher it is because what would we be saying as somebody goes from not from 10 years of education to 11 years of education. We're saying someone goes from female to male. Ooh, I'm not going from female to male. I would like to stay female. I would, absolutely. So we're saying, we're not saying that. That we know for sure. We're not saying that. But we are saying in this way that the variable is coded from 0 to 1, what we're saying is as that variable quote unquote goes up from female to male, that means males have a higher salary than female, right? If we were to look at the next one, we would say as it's going from white to black, so we would say blacks have a lower, because that's negative, a lower salary than whites. Okay, now, and then the last part, before I get into the dummy variable interpretations with interval level variables, one thing that, let me just get it out of the way, because it needs to be out of the way, is that with a dummy variable and another dummy variable, two dummy variables, we do absolutely nothing with it. Two dummy variables should in your mind say, shoot, I should have done a contingency table. Because contingency tables deal with what type of variables? Dummy variables. I mean, categorical variables, but dummy variables are categorical variables, right? So I should have said, I want to do a contingency table because that is where I look at categorical variables and their relationship. Okay? So this number is essentially telling us there are less black males in the sample than white females. There are less black males in the sample than all other categories, really. But this is a number about proportion. It tells us nothing about relationship, a number about proportion, okay? And so we should not be concerned about a correlation coefficient that has two, that's about two dummy variables. We should not be concerned about a correlation coefficient, an R value, that corresponds to two dummy variables. We, again, will not, should not, will never be concerned with such a value, okay? But let's go back to the interpretations of one dummy and one interval variable. All right, to do that, let us go to our word equation. I love word equations. They're so awesome. Okay, so what do we do here? Because we knew how to do it in our previous slide, right? Interpreting two interval variables. Again, we can use either. Here we go. We have interpreting an R for one interval and one dummy, okay? And how do we do that? We say, literally, if you follow this, there's no going wrong. And it's a matter of just understanding this interpretation and using it through every scenario that looks just like this. Because the only scenarios you'll have are variables with two intervals or with a dummy and interval. So I've given you both, right? So for our interval and dummy, this is how we would interpret it. We've got a dummy variable. What's the value for for one? In this case, we see the value for one is male. Okay, what's our value for 0? Here we go. Our value for 0, dummy variable value of 0 is female. We're clear? So, So what's our direction? Well, what's our interval variable? Our interval variable is salary. So our R is correlating salary with gender. Okay, same concept as the previous slide, but so we're just plugging in, and if the number is positive or negative, we say higher or lower. Just that simple. So here we go. We had an R, hypothetical R of 0.32. So what do we say? Based on our variables, right? Gender and salary, we say males because that's our one. So we say males have, it's a positive, so we say higher. Salary, because that's our second variable, our interval variable, then our dummy variable value of 0 is female, so we say female. So we are left with males have higher salary than females. If it's a negative value for R, males have a lower salary than females. what we would say, right, in a quiz, in an exam, because this is a learning environment and I need to make sure that you guys have this packed down, you would tell me what the direction is. For the first one, positive. For the second one, negative. You would tell me what the strength is. They're both the same number, 0.32, so hopefully you would tell me moderate. But then you wouldn't stop there, because I need you to know how to do this in a very diverse environment where everyone isn't as smart as you and knows all the stats in the world, right? So not just direction and strength, I need you to provide the layman's terms. So here it is. Males have higher salaries than females, or males have lower salaries than females, comma, but it's a pretty moderate relationship, not very strong, not very weak, right? Pretty moderate, okay? Males have higher salaries than females. Notice that both of the dummy variable values are in this very short interpretation. Males, females, because remember, this is a comparison of the dummy variable values. Males have higher salaries than females. Males have lower salaries than females. Mind you, a very moderate, of moderate strength. Just that simple, of moderate strength, right? So males might have a very moderate increase in salary than females. Okay. So let's do it for race. We had black equals 1, white equals 0. So what would we do here? Black equals 1, white equals 0, and it was 0.23 or something like that, right? So it was negative 0.23. So black equals, okay, so black equals 1, right? Here we are, black equals 1. It was a negative relationship, so we would probably say lower. It was a relationship with salary, and then our dummy variable value of 0 was white. So what would we say here? Blacks, right? Blacks have, we would say, lower salary than value of 0, whites. Blacks have lower salary than whites, given this is a weak relationship. Just like that. Now, I promise you, there are no tricks about this. So if you simply follow this word equation, I'm creating words apparently, this word creating terms, but it's a good term, word equation. If you follow this word equation with all that is in you, just memorize it and know that it never changes. I use this in my studies, right? This is how you read things in research articles and reports. So what you're learning is not just a word equation. This is real life. This is what we use, right? Because I have my mathematical mind, I guess, I was able to come up with some equation for it so that students who are in the learning process can quickly grasp the concept. Okay, so that is it. That's it. That's lecture 4 in a nutshell. Please do proceed on to the exercise, the homework, and I'll catch you later. Bye-bye.